The first question that I have is that it's for the speaker. It seems part of the drive in the market comes from telecom and from this idea that there will be more telephones and tablets than humans. But on the other hand, if you look at Internet of Things, you can think of 3 orders of magnitude more devices around. Now, if you do telecom circuits and the corresponding design automation for Internet of Things, the requirements are totally different. Kind of extreme low power, low bandwidth are really contrasted with the high bandwidth requirement of telephone. So how do you see this transition? You see that Internet of Things far away, you think that you can have a dual type of offering? What are your thoughts about that?
So let's just state where we are today, right? The big wafer volume driver, I think Ravi was showing those numbers, is actually the mobile. It's the terminal, right? The handset or whatever we want to call this thing. That's what the largest number of wafers are. Those are, in the meantime, the first adopters of technology, at least for foundries. Let's put Intel as an integrated company aside. Obviously, their business is driven by processors, at least from a volume perspective. I'm misquoting, probably in this. For this reason, they also become the lead customer for the foundries. If I'm a foundry, what I need is somebody to drive huge amounts of wafers through my fab, because the investment cost into the fab is becoming humongous. So I'm going and trying to capture an Apple, I'm trying to capture a Qualcomm, etc., as my first customer to lead the process development. So that's where we are today. Now the question is, what's going to happen once potentially the phone starts disintegrating, or and is a hub plus a bunch of things around it, some of them attached to the body probably, and you are the expert in this area, or if we're seeing more things connecting to some other sort of hub with each other, or with stuff that's very, very distant. Now these other things are much simpler, and in many cases these other things, are heavily reliant on a sensor. The sensor not being a microphone or our fingers, right, which is where most of the information is coming today, that's being related to the mobile phone. So for this reason, we need some technology which is adapted to sensors, and then from there the sensor signal goes into some conversion into digital, and from there it goes into digital processing, and then it lifts off again through some RF interface, probably to some hub, which continues conveying the information there. The aspect, maybe Ravi can comment a little bit on this, that I find interesting is you were talking about some analog companies pretty much being able to stay in the realm of analog and having a nice business there. I see it slightly differently, but you're the expert here, which is that in the end, all of this information needs to be processed, and then it needs to be sent off in the future. So I'm really doubtful that these guys who have an analog-only business are going to be able to survive over the long term. I think what's going to happen there is we're going to have the next race down to more slope, but starting again at the 0.3 micronode, or 130, 55 to 65 is today, and then getting very quick onto the 40 to 28. But how do you see that?
Yeah, no, I see it. So today the industry has catalog and ASSP. Catalog, analog being the companies like Dallas Semiconductor, Texas Instruments, now National Semiconductor, Maxim. It's really, that business has grown on the data book. You have a data book, you have a specific part, and that part is what gets sold. The ASSP, or Application Specific Standard Product, is where you have Qualcomm, Broadcom, NVIDIA, etc., and those are the ultra complex SoC folks. And I do agree that if we look at a time frame, say 20 years from now, what is a catalog part is going to dramatically change. Today, the catalog part is in the disintegration camp, and companies like Silicon Labs, IDT, and others are trying to integrate on 65, 55, and integrate a lot more intelligence on it. So I do think the catalog guys won't survive. But back to the point, what we see today, we have about 135 customers worldwide. And we see Internet of Things customers. The SoC complexity they build is nowhere near what's really being driven on the mobile end because of the application. So right now, I would say, if you look at Internet of Things, there's information processing SoCs where the information are things coming from sensors, temperature, pulse, pressure, etc. And a very simple build-up of that 6-component platform I talked about. And they are living and doing their design with existing design flows today. So where there's a missing link I strongly see is, if you look at what is the sensor, so if you look at the world of the MEMS designer and the tools they're using and how that comes together with EDA tools, unfortunately the link is not very good. The link is the MEMS tool generates a Verilog A model, and then you run that in your SPICE simulator, and together you can have SPICE plus Verilog A to simulate a MEMS transducer together with some electric circuitry. That's state of the art today. Could it be better? Could it be a lot more tightly integrated? Absolutely. But you're spanning many domains. You're going from mechanical to electrical. And that's a boundary which EDA has not crossed yet.
What's your opinion on that? Your talk was very much centered on the high performance system. So do you think that Intel and other companies will develop platforms to address a large multitude of low performance, low power devices?
For sure, we also want to go into or stay in the mass, yeah, but of course you need a differentiator, and of course you also need a challenge. And for me, from a wireless perspective, the Internet of Things is of course not such a challenge. So soft integration is. But if you look at the kind of connections you think there, then like SOCs for this type of communication exists for years already. I would also guess that integrating sensors and this type of thing is the main driver. But as this really becomes a mass market, that's naturally also the type of business that Intel wants to go into. And what I could expect is, then you're talking also about some things like ad hoc networking, and again, you have this verification problem, yeah, of how will your system interact with other systems. And I think in terms of that, that's for sure a challenge.
I'd like to ask a question in the direction of is a signal processor communication first. The network provider today asks us basically, or simply says, okay, the costs are so high for the spectrum, we only want spectrum around. So we want to exchange transmission power versus processing power. And if you look at our famous slide, Shannon Bean's board, actually it's not true. If you really analyze it now today, we have underutilized the silicon area. It's growing far slower. The reason is simply because the analog or the digital guys were smart enough to get the architecture that matches the digital technology. Now the question is the following. If you want to continue with high data rates, mobile communication, that's a huge market, and the service providers want us to push it to the limit, then energy efficiency is everything. So the question to all of them is then, what about energy efficiency? We want to increase basically for 4G. We need roughly tera operations per second, which is stupid measurement anyway, on 1 watt. Can we do this with this scaling technologies, not scaling with small technologies, or how can we achieve that? We have 1 watt. I don't think we have more than mobile.
I think we're already in the power limited design regime for ultra SoCs. If you look, we were in a frequency limited point for a while, and then we're in a power limited domain right now. So if I remember correctly, I remember a talk, I think it was actually someone from Intel who gave, that said if you look at the heat density currently inside a top-of-the-line processor, it's close to the heat density in a nuclear plant, in an ultra SoC today. So what that means is to be able to deliver what you just said, right? The question is, what do you need that terabit processing power for, or teraops of teraops of processing power for? Because fundamentally, I see, well, if you look at the applications right now, people say, well, what more will you want than video? Which is kind of comes back to, the statement, the market for a computer in the world is one, which a famous person from a certain company said before the computer era began. So I think the question is what is the application that will drive it? So some people say medical applications will drive it and more complex imaging applications, but you know, in such a case, do you really need to transmit that over a very wide distance or not? I think a lot of that is, the carrier's argument is very good, but they also are building picocells and microcells everywhere to be able to, to win that argument.
Okay.
I don't know, you have a different opinion.
I mean, the driver is not the higher data rate, the driver is the limited capacity.
Yeah.
And for many people in the world, the wireless computing will be the link into the World Wide Web. Yeah, so I think mobile computing will be really more used by more people than fixed web access. So in the long term, I think it's really the capacity, network capacity, which is the limit, and not the new applications driving for higher data rates. And there, of course, there are things you can do. Yeah? So interference is the big limit. So you're not alone in the world, but everybody is trying to use the same spectrum. And of course, there you can spend infinite complexity in order to combat that. Yeah?
But then you exchange exactly what I propose, or what the network provides.
The question is,
if you can gain 6 dB some transmission power, you get more customers, you get more money, and then throw all the silicon and all the complex signal processing, and then we have to live in 1 watt.
Well, there's some good news, at least on the process technology side.
Okay.
So if you're able to continue from a theoretical point of view, making the trade-off between power and signal processing complexity, at least on the signal processing complexity, FinFET opens up the door for more. Because what's happened to us is when we went from 28 to 20, I mean, if you look at Moore's law, basically, of course, there is an element to it, which is the economic one. Which pretty much, you go to the next generation, it doesn't cost you more. You get everything for free. You get more performance, you get lower power consumption, right? And everything comes at the same price. And higher density and everything comes at the same price. And since we all believe in it, it's been happening over and over and over from node to node to node. But this kind of was more difficult when going from 40 to 28. And it did not happen from 28 to 20. When we went from 28 to 20, we get more density. But we did not get more performance, and we did not get lower power consumption. Okay. So that trade-off suddenly, by going to the next process technology node, didn't do nothing. And that's also the reason why you see very little adoption of the 20 nanometer node. The only guys going to 20 nanometers in planar technology are the ones who needed integration density. A couple of mobile guys who just wanted to cram more CPUs and more GPUs with all the memory onto the chip. FinFET is the thing that gets us back onto the promise of, hey, it scales, so it gets smaller, and we get more performance, and we get all of this for less power, or some trade-off thereof. So in that sense, when we get onto the FinFET train, which some people already are on, we start benefiting from that, while we have to stay in the same power envelope.
I'm afraid they will demand from now on the tools that you were talking about. Mm-hmm. Because right now they are using the plain bread and butter cadence environment, and I know they will be demanding what you were showing. Now to my question, maybe this is more going in the direction of analog and digital, the convergence of analog and digital. I completely agree. The convergence is there on both sides. Now, on one side, we see more and more serious analog in chips that we traditionally consider as quote-unquote digital. There's no such thing anymore for a while. And then on the other side, we also see many of the very demanding analog tasks performed by essentially digital components. Ravi gave excellent examples of that. So my question is, at least I and many colleagues consider digital, especially circuit design, as an extremely conservative field, which is relatively closed to innovation. At the circuit level, transistor level, practically nothing happened for 30 years. Architecture level, well, slowly, slowly. On the other side, analog design, I always consider as very open to innovation and very open to adventure. Now that we see these two fields coming together, analog and digital, seriously coming together in very high demanding chips, where do you see, or how do you see the future? Do you see this combined, converged result becoming more open to innovation, or adopting some of the conservatism that was so traditional in digital?
Let me give you a very good example. We were talking about this just before, after my talk with a few of us here. We have an excellent example for this. We provide interfaces. Let's take USB. Right, I showed you the USB, we take the analog, we have to scale this thing, we kind of get it smaller, and it's a lot of work, we do all these tricks. We also have a USB controller. For the USB controller, we did it for, we had it at 130 nanometers, we had it in 90, we had it in 65, we had it in 40, and in principle, it's not really like this, because we have to add functionality. In principle, we just take design compiler, push the button, don't have to do anything. We get it implemented in, you want it in 20? We have USB controllers in 20, and I can anticipate that whenever some large IDM has a 10 nanometer process running, it needs our USB controller in 10 nanometers, they'll push the design compiler button and it'll work, if they want, right? And I will have done absolutely nothing. Right? The semiconductor vendor will have created the PDK, our friends in the implementation group will have done very little to the synthesis tool, a lot to the place and route tool, and things that work. So we can afford to be lazy. And that's where most of the innovation has been kind of at the computer architecture level, etc., etc., etc. On the analog side, the driver for our business, for instance, is not the catalog parts that Ravi was talking about, it's the leading edge SoCs. We can't just take our last design and say, ah, well, just fudge around the corners a little bit, will work in analog. We have to invent, we have to be creative. And the pressure is tremendous. The reason that the pressure is so high is that the disaggregation, as Ravi was explaining, is very expensive. Just saying, well, I'm going to take the USB PHY, and I'm not going to be integrating it into the 20 nanometer chip, but I'll just have a separate PHY chip, just kills you in terms of the bill of materials. And you have more space anyways. But it also kills in terms of the bill of materials. The way I asked once a customer, like, look, I mean, so how do you approach these things in terms of partitioning this into a separate analog chip and a digital analog? As long as I can buy it from you and put it on the digital, I'll put it on the digital.
So this means
it forces the creativity, and it's using, exactly, and it's using, and the funny thing is what's driving is the fact that we want to use processes that were analog design, but for digital design. That's absolutely funny. That's what's driving our creativity in the analog space. And it's also then the thing that's driving the analog guys to think, well, maybe I can get away doing less analog design and doing more digital, because that's really what the process was intended for.
And I'll just add my 2 cents, which is, when's the last time you saw a RTL designer be excited about using a delta sigma modulator for anything? I think the opportunity is huge. It's going to be very analog centric. You need to understand the function at the beginning. In fact, you may have no idea how a traditional buck converter worked, but the fact of the matter is you have currents and voltages, and you need to do information processing, and how are you going to use the key building blocks? It happens to be that some of these building blocks are in the ones and zeros world rather than in the continuous time world.
I would say you have innovation when you have problems, yes, and of course digital design developed exactly the way we wanted it in the last years. So we got our twice the gates each time we had a new design node. Okay, power now becomes a problem. Now you see, as we heard, in 40 nanometers, we will get some real innovations again also in digital standard cells. So that's what it drives. So you need a problem to solve.
There's a question up there.
Hi, so I'm Rakoshi from WTH Aachen. I'm a PhD student, and I design digital stuff. So my question to you is, because this analog world is getting the leading edge in the complexity, my question to you is, what can the digital world do to fix this? Because the digital world now is driven by the application domain. So you want faster SoCs, faster GPUs, faster everything. But is there a possibility for the digital world to create, for example, simulation-oriented specific hardware, which enhances the analog designer to do their work more efficiently? So these simulation clusters or some specific hardware which can cope with such complexity. Do you think there is a possible way to do that?
So I have a strong opinion on the subject, and I think it comes down to the following, which is, I think there's a lot that digital world can bring to analog design, a lot. I fundamentally think by not being an analog designer, coming in from the digital world, you're better suited for specific things. So, for example, the concept of test. It's surprising how foreign that concept is when you talk to even some expert analog designers. But when you talk to a digital designer, it's like, how could you live without this? It's running in my blood, right? And so how can analog test become a reality, or analog bits? Right? So I don't think it's even a question of building a box to make something. I think it's actually looking at some fundamental problems which, with a very unbiased and fresh perspective, with the benefit of experience in the application in another area, to be able to bring it to bear in the analog world. And that applies whether it's analog mixed signal, or RF. I mean, one of the biggest challenges we see today is there's a digitally controlled type of analog circuit. Who's supposed to verify it? The analog guy goes, hey, I did my spice, I'm done. The digital guy goes, well, this is not my circuit. You did the circuit. I can write all the RTL, but I don't know if it's working or not. Right? And it's one of these things, right? And
what does working mean?
So I think there's actually a lot of opportunity for people from the digital side to make not just contribution, but substantial and fundamental contributions in terms of analog design.
And sometimes I may add it's little things, comes really surprising, but when we introduced our high-speed SerDes, the first ones that were running at 2.5 gigahertz, we had built-in self-test. Because time on a digital tester is much cheaper than time on an analog tester, number one. And the more you can, if the only thing that you generate is just a good or bad signal, right, then your time on the digital tester decreases even more. Well, the concept was completely foreign to analog designers we went to talk to, because we had to go to talk to the guys who do this type of service with understanding. That's really interesting. The team that built it had a combination of digital and analog guys. It was the absolutely most normal thing in the world to do something like that. Sometimes it's really just to look at some other discipline with the know-how that you have, and then talk to the guy who really understands the other part and tell him, hey, why are you doing it this way? Instead of accepting that that's the way that things need to be done. Really interesting things happen when people from different disciplines get together and ask each other questions.
Just a short question, because this was something I was also going to ask. Yeah, the way you explained it looks like that actually the SPICE simulation capabilities are really limiting the innovation that we can do. And the question then would be, probably that was also a little bit what you intended. Could we have ASICs instead of standard processors? Being specific to what simulation needs you need in SPICE, speeding up simulation by order of magnitude. And will that then actually be a possibility to get a better quality of analog designs, because you can check more hypotheses at the same time?
So what, at least in our experience, what we've seen in the SPICE simulation history and in the industry is people have traditionally traded off performance for accuracy. And when they trade off performance for accuracy, they go from a time domain based approach to an event-driven based approach. And when they go to an event-driven based approach, and then they start using table lookup models for devices, you start being able to decompose the problem, and you can actually break up a circuit and simulate it. The problem occurs when you need the accuracy and the performance. So when you have the trade-off, what you described has happened, right? And probably Magma was the most successful company getting a very parallel digital fast-SPICE simulator successful.
Okay.
But in the traditional nanometer SPICE accurate world, where you need full SPICE accuracy, partitioning and being able to regroup the data, that problem is a very, very difficult problem to solve. And some people say it's impossible to solve, but I never want to use the word impossible, but that's a big limitation.
I'd like to just a direct question to Yusuf. I think what we're discussing right now is a fundamental one. In the last 30 years, which or even longer, I've been in the business, we had a very win-win situation between academia and industry. Your company, our company was a win-win. And Yusuf mentioned that okay, there's some very traditional thinking in certain circles. My question then is, and I think that's most important for our students in here, is, and also for the professors, is, do we still have that kind of close collaboration? I heard some statements from the CEO in the Silicon Valley that doesn't exist anymore. You know, they do some old, innovation is no longer at the university, they do some crummy stuff that's no longer interesting. So, what do you think about that? Don't be polite, just tell us.
I think we have an advantage because we're a small company. So, I mean, we collaborate with about 15 universities worldwide. Almost all of them right now are in the United States, just by reason of size and reach, and we focus on specific areas that map across the platform. And our job is to build the best tools and innovate in the tool area. We work with they're primarily design teams, circuit design teams, and work with them to develop new methodologies on if we have these types of analysis capabilities, what's the best way for design teams to build it. And I think it's a very big win-win between university and industry. I think a fundamental thing is the bigger the company gets, the harder it is for a lot of those things to happen. So that's, I don't know, my 2 cents.
Can I ask, I have a question which kind of builds on that, because a question of education of people, because we have seen from one side there is a lot of interest to have high performance analog mixed-signal design, so there will be a lot of interest of people who are educated in this field. So, but still, I always feel like they're lacking, like still you cannot see any, for example, book that talks about using FinFET, economic design, and things like that. So do you see in the future companies involving more in education or still leaving it to universities, and how it goes? I know Synopsys has a lot of programs on this. How do you see it, the development of education? Do you see more advancement in education of analog mixed-signal design in universities and worldwide?
So I do see more advancement going on there. I think today, the demand for mixed signal designers is astronomical. And just like everything, it will have its day. But I think this is the era, right, where mixed signal designers will have their pick of where they want to work. And I think fundamentally from the education perspective, there are, places where, newer and newer circuit techniques, a lot of research is going on into new innovative circuit design techniques for applications. A lot of that is limited by what process technology they get access to with their foundry partners, right? I mean, right now it seems like 65 is the barrier, and if you want to get to 28 or get a FinFET, stand in line, take a number, and we'll see you in 3 years.
Exactly, because it's hard to teach people in universities about these new things. So how
Absolutely. On the area that I'm driving within Synopsys, which is all designed for leading edge, I don't have hardly any cooperations with universities. Now, I'm probably the first one who would love to do that, but the issues that we face are the following one. If we want to take advantage of the university function as being ahead of what we're doing in development, we're doing research, maybe with some practical applicability about that, what it would mean is that the university would have to be doing research in the process node that's probably about 2 to 3 generations from the one that we're currently doing design on. We have no idea what that process node is going to look like. In fact, the industry doesn't know what that process node is going to look like. My friends to the left of me know a little bit sooner than everybody else, probably about 2 years ahead of everybody else, because they're 1 generation ahead of most of the foundries. That's acknowledged by everybody. But the visibility into what is the implementation technology going to be that we do the systems on chip on, mixed signal systems on chip on in 3 generations, we don't know. So I can't tell you, why don't you go and explore into this area? Then when it comes to access to silicon, assuming that you would want to do something with us in 20 or in 16 FinFET, I probably can't even get the non-disclosure agreement signed with you, because I'm in line, and the only reason that I'm in line is that my main customer is also their main customer and is in line, and probably is in line for the slot number 1. It's already a problem for the guy who's in line slot number 3 to get the information at the same time. Because the foundry says that, look, we can't handle that many guys, because we don't really know what this thing is going to be like. So it's very difficult for us to provide basically the foundation in terms of status. This is what you have to target, and this is what you have to be shooting for. I think things will change, or are changing, when we're looking at the not so new nodes. So when we're looking at the keyword of the Internet of Things was said, right? I immediately associate with that sensors and other things. Those things are being done in 65 nanometer nodes. Access to silicon is easy. A shuttle costs you 100K, 150K. I mean, you just pay for these things. They come back after 4 weeks. I mean, life is good. When you work in the 20 nanometer node, the shuttle costs you a lot. I'm not going to say how much it is, but I can share that it'll take today about 6 months until you get it back. If they can't process it, it may take 10 months until you get back for the first time, right? Which huge loops, so it's very unpractical, but I'm very hopeful that the Internet of Things may create again an opportunity for us to be working in semiconductor-based type of areas more with universities.
I feel this is very, very important because we, on the university side, we consistently have this difficulty of motivating our students with real examples or real design examples, rather than with, let's say, toy examples, looking at something that is really, really challenging. But the moment you go there, of course, you are facing these enormous silicon costs, and then that is a game stopper for us.
Yeah, so one of the things also following up on that, for many of these ultra SoC types of projects, one of the things I've seen is very successful in several US universities is a very strong alliance between a fabless SoC company and a pool of universities. And there's literally a rotating door of students going in, and they're working on a block, supporting someone working on, for example, the RTR 8600 I showed, someone working on a piece of that. Ultimately, I think right now that's the only type of experience that someone can get. But it requires a very, very strong alignment and a partnership, frankly, which is going to start extending over several years, where the fight for mixed-signal talent is brutal. So by establishing a connection and an escalator of talent going into the company and participating, and seeing they can play on that, that's an ability for them to recruit. And I've seen that very successfully done by the top 5 fabless companies, and that may be, what needs to happen here. I don't know how much it already does. It maybe it does, in which case.
There's a question up there.
Just a comment, it's exactly the way it worked when we worked together with Synopsys. We founded this company, it's exactly the model. On the academic side, we have to push for that, Nobody's going to give us anything if you sit here. I'm not saying you do that, if you're sitting here and expecting our genius is rewarded by visits of industry. I think we also have to push for that. And then it works. We did it with Synopsys and twice.
At that time, that was a breakthrough technology, which really gave a big added value to the industry. So it was really really innovation. And what doesn't work is like offshoring some tasks to universities. And at the point where you're actually doing the same that we are also doing, it's hard to collaborate for other reasons than to have contact and to get some people, because you've seen the complexity of the stuff we are dealing with, and we have huge teams there. And the other problem is IP. Yes, so the IP battles everywhere, and owning the IP in the end is really essential for the companies. So it's better to do it yourself, not to be in any free zone there. It has to work, yeah. And typically, when you have a collaboration at the end, when your boss asks you, okay, so you guarantee me it works under any circumstances and we are not violating any other IP, then you say, okay, I maybe do it myself again. That's a big problem. So if you do real forefront innovation, then it works. Like, give us a new methodology, like the one I'm looking for, or
let's take one last question.
Stuff like that.
Thank you. Boris Brad, PFL. Thank you very much. Really interesting educational talks. So there are, obvious, well-known reasons to go from analog to digital, right? I mean, it's design complexity, more area, power efficient, testability, and so forth, right? These are well established. So I come from the architecture community, and in the last couple of years, there have been quite a few calls basically saying that for efficiency reasons, that is power efficiency, we should go from digital to analog because certain functions are so incredibly efficient and easy to do natural, right, in analog. And of course, you talk to a designer and you tell them that, and you're just like, this is insane, right? But the differences are literally order of magnitude. So the question is, are you seeing among your customers anybody actually experimenting with this, going from digital to analog, and sort of, what are your thoughts on that?
I'll say the best example is you look at the history of the 10G base T standards discussion, where there's literally a battle between people who wanted to do continuous time equalization and digital equalization with some pre-conditioning. And there were arguments about power, there were arguments about area, arguments about what was robust. Ultimately, the standard does not dictate what your implementation is. So at the end of the day, it's really a show of how far can you push one technology versus the other. The arguments that have been made regarding the power, I think at the end of the day, need to sit in the context of what is a total system power budget and versus what is the power of implementation A, which is analog rich, digital poor, and implementation B, which is digital rich and analog poor. And looking at them in isolation is one thing, but looking at them in the context of the system is a very, very important thing that a lot of people miss. And in the context of the 10G base T standard discussion, in the context of the system, there's a driver. That driver is sucking up a lot of power. Right? Similarly, in radio transceivers, people are arguing versus one transceiver structure versus another. The power amplifier is going to really dwarf everything. So taking it in the context of the system is really the next thing that needs to happen before the statement that the architecture is better one way versus the other.
Comments from others from the panelists? Would like to add some final comment? Well, in this case, I like
this is a great time to be inside the design.
Yeah. It's, the technology is just fascinating, right? And it kind of always looks like we're going to be hitting the wall, and then we're able to break through the wall again. Now I know that lots of us are starting to be concerned, some late at night after not having slept for very long, about, well, maybe we're going to be hitting the end of all of this at 4 nanometers, and then what are we going to do then? We'll figure out something. We have plenty of time. We've been at this point many, many times. I mean, in fact, every time that we get a new processor, we scratch our heads and say, like, how are we going to do anything? Because, and you see the chips coming, right? And there are stuff that we all love to use every day. So I'm very excited about the future.
We hear the talks that we'll never have devices smaller than 1 micron.
Yes.
Exactly. Okay. Okay, I would like to thank the panelists for their lectures as well as for their availability for the discussion. I'd like to thank the audience for being here and now tell CH for sponsoring this event.